Hi everyone. So we are back with another video for chapter 8, that's your D and F block elements. So in the previous video we have already spoken about transition elements and few properties we discussed. So let us go ahead with another very important property of atomic radii. Okay, hope it is clear to you. Okay, so when we talk about atomic radii, we already have an idea that when we move across the period, the atomic radii decreases. And down the group, atomic radii increases, which we have learned in P block. But here, it's not like that. What actually happens, the atomic radii first decreases in each series. In the middle of the series, it becomes almost constant, and further towards the end of the period, it increases. Let me take a graph for you so that you understand it better. Okay, here we have a graph to make things a bit more clear. Let me fix it for you. Yeah, here we go. So if you see here, we have clearly mentioned about 3D, 4D and 5D series. So this green line is depicting your 3D series, blue line depicts your 4D and the red one depicts your 5D series. Let me take an example of 3D series. So scandium to chromium, the atomic radii decreases. In the middle, like for iron, cobalt and nickel, it's almost constant, and suddenly it increases for copper and zinc. So this variation is not only existing in 3D series, but it is very true for 4D and equally valid for 5D series. This is one important concept. So what is the reason behind it? Let us look into the reason. So what do we do as we move across the period? We are adding one electron but to the same shell. That's a concept what we have got from our understanding of variation of atomic radii. So the number of shell doesn't increase, but the nuclear charge is increasing. That's what is highlighted here. Nuclear charge increases, but the number of shell doesn't increase. So what happens? The force of attraction would be high. Force of attraction of the nucleus for the valence electrons would be high. Therefore, there is a slight contraction from scandium to chromium. But what happens in the middle when we talk about iron, cobalt and nickel? I said the atomic radii doesn't change practically. It's almost the same. So this is because when we are adding the electron, okay, when we are moving from iron, cobalt and nickel, electrons are getting added as well as protons are getting added. So the nuclear charge is increasing. But at the same time, when we keep on adding the electrons, there is something called as shielding effect. Shielding means protection or intervention, or you can say these electrons which are added to the inner shells, which are closer to the nucleus, act as a barrier for the outer electrons. Let me give you a brief idea. If suppose this is a nucleus, this is the intervening shell for you, and this is the valence shell for you, right? So as from iron, cobalt and nickel, we are adding one electron to each. So the positivity of this nucleus for the valence electrons would get reduced. Why will it get reduced? Because more number of electrons are between this nucleus and the valence electrons. So as the number increases in these shells, the inner shells, they act as a barrier. They act as a barrier between the nucleus and the outermost electron. That effect is called as shielding effect. So what happens, whatever is the increase in the nuclear charge, it is equibalanced by the intervening electrons as shielding effect. Hence it gets nullified. Therefore, what contraction we were observing in the atomic radii due to increase in nuclear charge is counterbalanced by the shielding effect for iron, cobalt and nickel. Therefore, practically the atomic size remains same. But when you move to copper and zinc, so many electrons are intervened between the nucleus and the valence electrons that electronic repulsive forces start dominating the shielding effect. And when the electronic repulsion increases, the size becomes bigger. Hence, for copper and zinc, the size increases. So hope it is very much clear to you with the help of this figure and the effects. Now, very important question which you get in board exam is about lanthanoid contraction. So what exactly is lanthanoid contraction and where is it used? Now see here, we are talking about 3D, 4D and 5D series. That means we are moving down the group, okay? And we know when we move down the group, the atomic size should increase because the number of shells keep on increasing. But it's very clearly mentioned here, the size of the elements of 4D series is almost the same as the elements of 5D series. This is because of lanthanoid contraction. Now what exactly in a simple language I can make you understand about lanthanoid contraction is these intervening means the electrons which are coming in between the nucleus and the valence electrons. So we have already learned before that there is a gap in 5D series. After lanthanum, the elements have been placed below the periodic table, which I told you before that they are radioactive in nature. Hence, they have been taken out, okay, from the 5D series. So, all such elements which are placed below the periodic table as lanthanoids, they possess the filling of 4f orbital, okay. So since 4f orbital starts intervening between the nucleus and the valence electrons, therefore there is a concept called as lanthanoid contraction. That means the size starts decreasing. So you must be wondering, when shielding effect is increasing, the size should have been more, right? But actually what happens, very important point to remember here is these intervening electrons, I'll highlight it for you. These intervening electrons of 4f orbital show a very poor shielding. I've written here, they show a very poor shielding. So if they show poor shielding, will they be able to act as a good barrier or a poor barrier? Of course, a very feeble barrier. So the electronic attraction and the nuclear protonic attraction for each other will be so strong that the atomic size for 5D series practically starts decreasing and becomes equivalent to that of 4D series. So remember two very important concepts, that these intervening 4f orbital electrons show a very poor shielding effect. And since these 4f orbital, intervening 4f orbital have a very poor shielding, they are not able to reduce the force of attraction of the nucleus for the valence electrons. So since they are not able to reduce the nuclear force of attraction, therefore there is a compression in atomic radii, and that is known as lanthanoid contraction. So hopefully I made it very clear to you. Let us go ahead. That's a very important FAQ. What is lanthanoid contraction? What are the consequences of lanthanoid contraction? So lanthanoid contraction I have already discussed with you. I'm not explaining you again. You can read the text here and make a note of it and when you're testing yourself as a self-test, then such answers should be written. Okay, so this is for your reference. Now, this I would like to discuss right now, the consequences. So the first consequences, amongst the consequences, the first one is the similarity in the properties of second and third transition series. We have just now learned that the atomic radii of 4D series and 5D series is almost the same. That was because of lanthanoid contraction. Another very important thing is separation of lanthanoids. Yes, that also we have spoken about, that lanthanoids had no place in the periodic table and therefore they were placed at the bottom of the periodic table. Very important, another concept is, due to this lanthanoid contraction, what we have discussed, that the poor shielding effect of 4f orbital electrons, the nuclear force would be very, very strong for the valence electrons. It affects the basic strength of lanthanoid hydroxides. So when we talk about hydroxides of this lanthanoid series, the variation is like this. That is, the basic strength decreases. I said the basicity decreases from lanthanum to lutetium. Lanthanum we have already discussed. Lutetium I showed you in the periodic table. That's the last element of lanthanoid series. So it decreases from lanthanum hydroxide to lutetium hydroxide. So that's very important board question. Please learn it well. Okay, we'll go ahead. Here I have another 3 to 4 FAQs for you. So you will be writing the answers of these questions in your notebook. Okay. After I finish my video, you will write the answers, and before we begin the next video, we'll discuss the answers. So all these questions you'll be able to do because I have already spoken about all such properties. Fine. Now let us go ahead. Quickly let me erase this for you. Okay. Let me talk about enthalpy of atomization. So what exactly is meant by enthalpy of atomization? You can see here the graph is clearly evident. The green one again is for 3D series. Okay, I'll write here. Blue is for 4D and the red one is again for 5D series. So as we move down the series, the enthalpy of atomization increases. The reason being, as we move down the series, the number of valence electrons increases. And since the valence electron increases, the protons inside the nucleus are also increasing. Therefore, the interatomic attraction of the nucleus for these electrons would be very, very strong. And since this attraction will be strong, therefore it will result in high enthalpies of atomization. That is, there will be a strong bonding between the atoms. Okay. Next property over here we have discussed is ionization enthalpy. So we know that it's the enthalpy required for the removal of the electrons from the valence shell. So what do you think? Very important. As the nuclear charge increases, the ionization energy should also increase, because it should be very difficult to remove the valence electron if there is a strong force of attraction between the nucleus and the electrons. Of course, we are talking about the valence electrons. So remember, again there is a deviation, and again it is because of lanthanoid contraction, that was poor shielding of 4f electrons. So because of lanthanoid contraction, the ionization enthalpy of 5D series is higher than 3D and 4D series. Okay, though it should have been lower, because as we move down the group, the atomic size should increase, but we already saw there in the previous slide that the atomic radii of 4D series was just the same as 5D series because of lanthanoid contraction. Hence, ionization enthalpy is also slightly higher of 5D than 4D and 3D. Let me set another slide for you. Yeah. What are the applications of this ionization energy? Very important board questions will be asked from here. So understand it very carefully. Ionization enthalpy actually decides the oxidation state of the metal atom. Indeed, it talks about the stability of the oxidation state. So which metal will tend to remain in which state is calculated on the basis of ionization enthalpy. So what you need to keep in mind, the key sentence is the metal state for which the sum of ionization energy is less seems to be more stable. Let me explain you this concept with the help of an example. Let us take that nickel which is in zero state, okay, is getting changed to nickel plus 2. That means here it's a process of oxidation because it is changing from lower state to the higher state. So on the basis of the ionization enthalpy chart, we calculated the sum of the first ionization enthalpy and the second ionization enthalpy, and we found it to be 2.49 into 10 to the power 3 kilojoules per mole. Wherein when nickel tends to change from its zero state to plus 4 state, that means plus 4 means 4 times we'll have to remove the electron. So we'll have to calculate 4 enthalpies. Here why we calculated 2 enthalpies? Because we are moving to plus 2 state. That means removing the electrons twice. So here 4 times when we remove the electrons, okay, so we calculated the sum of 4 ionization enthalpy. That means 4 electrons have to be removed from the valence shell. So the sum was found to be 11.299 into 10 to the power 3 kilojoules per mole. Now compare. What do you think? Which state should be more stable? Nickel to nickel 2 or nickel to plus 4? Of course, nickel 2 has the lower ionization enthalpy than nickel 4. This is one concept. But the question they don't ask like that. They compare two different metals with each other. So, but the state remaining the same. So that's why first let us compare nickel with platinum in plus 2 state itself. So when nickel was converting to plus 2 state, ionization enthalpy was found to be this, the sum of 2 ionization enthalpies. Likewise, when platinum was converting to platinum 2, the sum of ionization energies was found to be this, 2.66 into 10 to the power 3 kilojoules per mole. If you compare these two, which is a smaller value, of course, 2.49. Henceforth, nickel 2 state is more stable than platinum 2 state. That's very, very important question. So I'll highlight it here for you. I've written here, nickel 2 state has less sum of ionization enthalpies, therefore it is more stable. Can you relate this concept with this statement what we learned here? Yes, it goes very well in coordination. So here is the answer for this reason. Next, if you compare now nickel and platinum in their plus 4 state. Again, very clearly evident, if you sum up, now the 4 ionization enthalpies sum up in platinum to give a lesser number than in nickel. Hence, platinum 4 state is more stable than nickel 4 state. So that's very, very important board question. Okay. So remember all the things whatever we have learned today. We spoke about just a summarizing part. We spoke about the ionization enthalpies, enthalpy of atomization we spoke about. We also discussed about lanthanoid contraction, its consequences, and how there is a variation of atomic radii across the series and down within the series, right? So all these concepts have been explained very well. So learn it and keep in touch for the next video. We'll watch soon. Thank you.